By the late 18th century, combustion had been studied extensively. The gases, carbon dioxide, nitrogen, hydrogen, and oxygen had been discovered, and the list of elements continued to grow. However, it was Antoine Lavoisier, a French chemist, who finally explained the true nature of combustion, thus clearing the way for tremendous progress that was made near the end of the 18th century. Lavoisier, like Boyle, regarded measurement as the essential operation of chemistry. His experiments, in which he carefully weighed the reactants and produced products of various reactions, suggested that the mass is neither created nor destroyed. Lavoisier's verification of this law of conservation of mass was the basis for the development in chemistry in the 19th century. Mass is neither created nor destroyed in a chemical reaction. Lavoisier's quantitative experiments showed that combustion involved oxygen, which Lavoisier named phlogiston. He also discovered that life was supported by a process that also involved oxygen and was similar in many ways to combustion. In 1789, Lavoisier published the first modern chemistry textbook, Elementary Treatise on Chemistry, in which he presented a unified picture of the chemical knowledge assembled up to that time. Unfortunately, in the same year the text was published, the French Revolution broke out. Lavoisier, who had been associated with collecting taxes for the government, was executed on the guillotine as an enemy of the people in 1794. After 1800, chemistry was dominated by scientists who were following Lavoisier's lead, performed careful weighing experiments to study the course of chemical reactions and to determine the composition of various chemical compounds. One of these chemists, a Frenchman, Joseph Proust, showed that a given compound always contains exactly the same proportion of elements by mass. For example, Proust found that a substance, copper carbonate, is always 5.3 parts copper to 4 parts oxygen and 1 part carbon by mass. The principle of the constant composition of compounds, originally called Proust's law, is now known as the law of definite proportion. A given compound always contains exactly the same proportion of elements by mass. Proust's discovery stimulated John Dalton, an English school teacher, to think about atoms as the particles that might compose elements. Dalton reasoned that if elements were composed of many tiny individual particles, a given compound should always contain the same combination of these atoms. This concept explained why the same relative masses of elements were always found in a given compound. But Dalton discovered another principle that had convinced him even more of the existence of atoms. He noted, for example, that oxygen and carbon form two different compounds that contain different relative amounts of carbon and oxygen, as shown in the following data. Dalton noted that compound 2 contained twice as much oxygen per gram as carbon for 1, a fact that could easily be explained in terms of atoms. Compound 1 might be CO, and compound 2 might be CO2. This principle, which was found to apply to compounds of other elements, as well as being known as the law of multiple proportions. When two elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. To make sure the significance of this observation is clear, in example 2.1, we will consider data for a series of compounds consisting of nitrogen and oxygen. The significance of the data in example 2.1 is that compound A contains twice as much nitrogen per gram of oxygen as does compound B, and the compound B contains twice as much nitrogen per gram of oxygen as does compound C. These data can be explained readily as the substances are composed of molecules made up of nitrogen atoms and oxygen atoms. For example, one set of possibilities for compounds A, B, and C's is. Now we can see that the compound A contains 2 atoms of N for every atom of O, whereas compound B contains 1 atom of N per atom of O. That is, compound A contains twice as much per given amount of oxygen as does a compound B. Similarly, since compound B contains 1 N per O and compound C contains 1 N per 2 O's, the nitrogen content of compound C per given amount of oxygen is half that of compound B. Another set of compounds that fits the data is example 2.1. See if you can come up with another set of compounds that satisfies the data in example 2.1. How many more possibilities are there? In fact, an infinite number of other possibilities exists. Dalton could not deduce absolute formulas for the available data on relative masses. However, the data on the composition of compounds in terms of the relative masses of the elements supported his hypothesis that each element consisted of a certain type of atom and that compounds were formed from specific combinations of atoms.